So again, I'm going to quickly list our givens here. Theta is 23 degrees. I'm going to orient the board first, actually. Let's do that real quick. So theta was 23. VI was 4 meters per second.
Wait, so this is the whole paper that you're going to use?
Sabella, go ahead.
Wait, that's not how wide is YI? 8. Oh.
Because the person starts at a height of 8 meters on the diving platform. That's pretty much all we've got for this problem. Now, so we're going to see here, we want to figure out the speed the instant before hitting the water. So we call that VF. So let's write VF equals question mark now. Turn off all of it?
Just open the shades though.
It's fine, it's fine.
No, I don't want the shades open.
Be nice.
No, Nicole, no.
We have the same birthday, you know. It's a bond. It's a bond.
I'm going to send my crew after you. I love that laugh.
I'm wondering what Steph's crew would be like. That's what I'm
We
wondering.
have that one at the moment. I'm going to get one.
Gabby volunteered at lunch.
Daddy, look, Mom.
All right, so right away, for all of these problems, think about conservation of energy. The energy in the beginning equals the energy at the end. So we start, and we think in our mind. You don't have to draw this, but this is what I'm thinking about right now. Here's the diving board. Here's the water at the bottom. Here's the person at the top of the diving board. At the top, the person has height. So the person has some sort of potential energy in the beginning. The person also jumps with a velocity of 4. So the person must also have a kinetic energy in the beginning. So that's what we know about the beginning of the problem.
Wait, why would he have kinetic energy if he's not even jumping yet?
He is though. Take a look, Bill. It says he jumps with a velocity of 4 meters per second.
Oh.
So we're saying like he's jumping off the diving board 4 meters per second, thus having kinetic energy. At the bottom, is there any height at the bottom?
No.
No. So there's no potential energy down here, but there is kinetic energy at the end, and that's what we're trying to figure out so we can find the velocity at the end of the problem. Erica.
But if he's going into water, isn't that like, don't you have you have energy when you enter the water?
Yeah, but we're considering, remember we said in the beginning, you always have to call something ground level. So I'm calling this ground level. So that's your 0 height mark. So if there's no height there, theoretically, then there's no energy there, potentially.
So if the velocity was 0, then there wouldn't be a KE.
Exactly. If he just went like this, watch. If he just walked off the end of the board without jumping at 4 meters per second, KEI would be 0, because there would be no VI. Okay? So imagine he just walks off the board, that means he's got no velocity to start. He just literally fell off like that. So there'd be no initial velocity, so there'd be no initial kinetic energy. Remember, kinetic energy only exists when velocity exists.
How would you know to put that as KEF though?
Because we're trying to search for the final velocity. The only energy part that has to do with velocity is the kinetic energy. So if we're looking for the final velocity, it means we must also be using the kinetic energy at the end.
Wait, KE only exists when what?
When there's motion, when there's velocity.
So then,
So there's velocity in the beginning. So there's KE in the beginning right here. There's going to be velocity at the end. We're figuring that out. So there's KE at the end also.
but if KE was 0, then there would be no KEF.
Correct. If velocity was 0, there'd be no KE.
Okay.
So let's write our equation. We write the beginning stuff here equals the stuff at the end. So in the beginning we have potential energy and we have kinetic energy. At the end, all we have is kinetic energy. There is no potential energy at the end because the person is at the water level. And we're considering the water level to be the ground. So here we have the beginning, these two parts at the top of the board, and then at the bottom by the water, this part here. There are no springs involved, even though I know a diving board is kind of like a spring. If you jump off of one, it does spring.
Platforms are.
But, oh, that's perfect actually. This is a platform, and that's exactly why I did that. Right.
Welcome.
So since it's a platform, it's not a spring. Yeah, a platform is a sturdy object, right? So the person is just jumping off of an object that is stationary. If there had been a spring involved, we would need 1/2 kx squared in that position. So let's write our equations out, please. Again, we're solving for VF. This becomes mgyi. This board is not agreeing with me today, so bear with me.
Do you have a pencil sharpener?
Not in this room, Seville, no. Unless there's somebody else in here. Mine's at 302.
What's that 302? I'm just kidding.
Pencil sharpener. So please, write down your formulas right away. You know these formulas. You should know them by now. They'll be given to you on the test, but you should really have them memorized at this point. Okay? Potential energy is always mgy. Kinetic energy is always 1/2 mv squared. I'm putting the subscripts in here, okay, to denote initial and final. That's the only reason you see the I and the F. Now, the next chapter we're going to learn, so tomorrow we're going to go into section 5.4, but then next week we're going to start chapter 6. And in chapter 6, we're going to talk about initial and final a lot. So we're going to have a lot of subscripts, so just get used to that. Okay, get used to the subscripts. Now, I'm going to erase this so we have more room. At this point in time, we want to take a look at our equation. What do you notice is in every part? Mass. So what can I do, Erica?
Cancel out.
Again, this only works because the mass is in all 3 parts. The mass is in all of the parts here. That's why this will work.
But wouldn't it not work because it's in 3 and not 2? Like, it's not even, so wouldn't you be able to cross out 1 on each side of the equal sign?
What about this? Think about it this way, Steph. Factor out a m. You have gyi over here.
Oh,
And on this side, if you were to, you have gyi plus 1/2 vi squared. And on this side, you can technically factor out an m also. And see how the m factors out on both sides? That's why they can cancel, really. Okay? That's the reason. So what we're left with is what we see inside the parentheses here. The masses cancel, and we're left with,
But there's 2 M's.
that's what she just says. There's m here and there's m here. If you factor the m out, it comes out in front. And if you think about this, take the m out in front. If there's an m in front here and an m in front here, they're
And if you
factors.
factor it out, both of the M's is not going to multiply and make M squared.
No. It's like if you have like 2x plus 7x. You can technically factor out an x and make it x and then 2 plus 7. Okay? So we cancel the m's. This is what we're left with. What are we trying to find in this problem?
B, yeah.
The f over here, right? So how do I get rid of this 1/2?
Multiply by 2.
Multiply by 2. So multiply this whole side by 2. And multiply this whole side by 2. On the left side, I'm going to distribute the 2. I'm going to get 2gyi plus, and now the 2 times the 1/2 just becomes nothing, or 1, or non-existent. Okay, that's what we're going to get. Again, take a look here. The 2 times the gyi becomes 2gyi. 2 times 1/2 cancel, and you're left with just the vi squared. Over here, we got rid of the 1/2 by multiplying by 2, leaving us just the vf squared. What do I do for the last step to find vf? Square root both sides. Square root, put a plus or minus out in front. That cancels the square factor there on the end. So that's our solution for the final velocity. 2gyi plus vi squared, all under a square root.
Wait,
And
why
now
did
you
you
just-
run that 2?
Why did I or what?
Why didn't you?
I did, but look, so Bill, I'm just ignoring it. I could do it, but I'm not showing it. Like this. And then the square root and the square cancel to become just VF.
Yeah.
I'm just kind of not writing that out. Okay? So if you plug in numbers now, you plug in numbers for G is 9.81, yi is 8 meters, vi is given as 4. Plugging in all those numbers, taking the square root, we're going to get plus or minus 13.15. You should be checking this on your own, so I assume everybody's doing this here. Okay, plus or minus, please. Now that's the velocity at the end. Plus or minus 13.15. Again, what did I do? We plugged in here, we plugged in here, we plugged in here with all of our givens to get this answer. So it can be either of them. But Armstrong said, what is the speed? The speed the instant. So the speed is always the positive value. Speed is the positive value here. Okay, so the speed is 13.15 meters per second. Any questions on this problem? Okay, again, these problems are the same every single time. All you do is energy before and energy after. It matters about the problem itself, though. If there's a spring involved, you throw on the one-hand mechanics squared. If there's potential energy, it's mg1. If there's kinetic, it's 1/2 mv squared. So think about what's involved in the problem and just list them.
What happened to the theta?
Okay, very good question, Seth. What happened to theta here? In this problem, if I wanted to solve this old school methods, meaning using projectiles and looking at the angle, we'd have to do like sine of 23 degrees, cosine of 23 to get our different components, and then use our kinematic equations. That's where the theta comes into play. But we solved this problem using energy methods, which is a little bit easier, I think, than using x direction, y direction, moving over our linking variables. So on your midterm, you're going to be given questions that can be solved either using kinematics, which we did in chapter 3 with projectile motion, or you can solve it using energy. If you have an option, I would choose energy. Energy is usually easier.
Yeah, this is a lot
Okay.
easier.
Now, the one thing this doesn't give you, though, is this. Think about this problem. The person jumped from the platform at an angle of 23. So this person is going to follow this kind of a path. So what we're getting as an answer here is the velocity 13.15 at this angle right here. We're not getting the x component or the y component anymore. We're getting the overall velocity at the bottom, right down here, when the person lands in the water. As opposed to when we did with projectiles, we would get the velocity in the x at the end, the velocity in the y at the end, and then we could always put those together.
Will there ever be a case when we can't cross out the
Yeah, the next example we're going to do. Remember last class I said, if you have a spring involved, there's no m in the formula, that's when it won't work, and you're going to see that in the next example. You had a question? I thought you had a question. You sure?
Me?
No? Huh. I thought you guys had a question. I heard you say, oh, ask him, ask him.
No, I said this is easy, or like.
And the other one? I
Well,
agree.
no, I just said this is surprisingly easy.
I'm glad you heard. This is a long problem to write. Really long to
Don't
write.
think I'm gonna do it.
Okay? If you don't want to write it, you don't have to. I'm not going to force you, but I'm going to give you about a minute or two to just sit here and write it. Okay? I'll dictate slowly. I'm going to dictate. So, I'm going to dictate. See,
I watched 4 episodes of
You-
Homeland last night, just in case you care.
you
Yeah,
want,
why are you so creeped out that I know that by
you
the
want
way?
to shoot.
You've been into our entire homeroom.
You want to shoot a rubber band. You want to shoot a rubber band whose mass is, in parentheses there, 3 grams. So you take a rubber band. Sorry, so you want to shoot a rubber band, parentheses, 3 grams mass. Across the schoolyard. So again, you want to shoot a rubber band with a mass of 3 grams in parentheses here. Okay, across the schoolyard. Another parentheses. From an elevated window 7 meters above the ground. At a classmate who's 2 meters tall. Which is like 6.5 feet. Maybe a little more than 6.5. So maybe somebody pretty tall.
I am. I thought
Okay, somebody who's 2 meters tall. Now, you know that you can stretch the rubber band. You know that you can stretch the rubber band, so think about like you're pulling back on a rubber band right now, okay? You can stretch the rubber band a distance of 10 centimeters. As we go through this, I'm going to underline things. Exactly. Oh, the board is really not agreeing at all. It's way off. Anyway, forget about underlining for now. If the rubber band has a spring constant, remember that's the flexibility of the spring. So it determines if the spring is a very strong spring or a very weak spring. What is a rubber band, weak or strong as a spring? Think about it, pretty weak, right? Can't you stretch a rubber band very easily? And you think about other springs. Take another spring and try and really stretch it really far. It's
Paper.
probably tougher to do that, right?
Paper.
Okay?
Paper is not a
Paper's not a spring.
But it's hard to stretch.
I guess it could be considered a spring because it does stretch a little. Everything is really a spring. That's something you learn in engineering. You can model anything in the universe as a spring.
This is what I'm talking
Because
about.
everything vibrates at a certain frequency. Now,
physicist over there. I watched some.
if the rubber has a spring constant of 0.2 newtons per meter, that's the K value, and you want it to hit your friend with a velocity of 12 meters per second, you want it to hit your friend with a velocity of 12 meters per second, low enough so that no one gets hurt, in parentheses, not parentheses. With what speed should you shoot the rubber band? With what speed should you shoot it?
So we're looking for VI.
Very good, Steph.
So this problem has like the one
It's
half.
got a lot going on, yeah. We got kinetic energy, we got potential, we've got spring energy, there's a lot of things. So we have to just list what we know. So what I'm going to do is this. I'm going to look at the problem and I'm going to think logically for a second. The person is standing at a windowsill, elevated. So he or she has potential energy. The person is also pulling back on a spring in the form of a rubber band. So he or she has potential energy of a spring. The person is also giving the rubber band some initial velocity, some sort of like a flick, if you will. Okay? So it's giving it initial velocity. So it has all types of energy in the beginning. It's got kinetic, potential, and potential in a spring. At the bottom, I'm not 2 meters tall, but imagine I was 2 meters tall. So I'm the 6.5-foot person at the bottom. If it hits me, and the goal is to hit, did I say hit in the head? I didn't say that, right?
No.
Hit him in the head, that's what I want to say. So if the person gets hit in the head, when the rubber band hits you in the head here, it's at a height of 2 meters. So there's potential energy at the end still, and there's kinetic energy at the end, because it's still moving. It's moving at a speed of 12 meters per second when it hits you. But there's no spring at the bottom, so we don't have to worry about the spring there. So what we know for this problem is in the beginning, there is potential energy in the beginning, there is potential energy in the spring, which is the rubber band, in the beginning, because you're pulling it back in the beginning. There is also kinetic energy in the beginning, which is what we're trying to figure out. We're trying to figure out VI. We know at the end, it hits a person who's 2 meters tall in the head. So it still has potential energy because it still is 2 meters tall. And it still has kinetic energy because it hits the person with some velocity. So that's my equation for this problem. It's a lot more detailed, but it's no more difficult than the last one was. It's just that there's more variables now. That's it. And the one thing that's tough is you can't cancel M now. Notice where's M missing? It's missing right here in the middle. So,
Why would you put that there, not on the other side?
because where was the spring? Were you stretching the rubber band in the beginning or at the end? So it goes in the beginning. Okay? Again, you're stretching it in the beginning of the problem.
Oh, so
Oh, it's not
KX is the 10 centimeters?
It has to do with the centimeters, 10, and the compression or the constant of 0.2.
Wait, so where you put the 1/2 KX matters?
It does, because if you put it on that side, it would be as if it was landing and then getting stretched. Where it's not. It's being stretched so that it can actually be launched. Now, some things to identify before we go any further. First, a lot of your numbers here are not in standard units, so please rewrite this right here as 0.003 kilograms for your mass. Because grams are not standard. Here, the distance that it stretched, x, this distance stretched, 10 centimeters. Rewrite that as 0.1 meters. Everything else is in standard units, but last class a lot of people messed that part up. Okay? Not in here, in the other class, a lot of people forgot to actually change the numbers, and the answer they were getting didn't make sense. Okay? So, what is the goal of this problem? To figure out with what speed should you shoot it with, which is VI. So we are searching to solve for this variable right here, VI. Now, to do that, we want to think about the fact that we don't have mass in everything, so we can't just cancel the m's anymore. So I want to take this and subtract them over to the other side of the equation.
Wait, can we list our givens first? Because I don't know any numbers. Did we go through those already?
We didn't, because they're in the problem. I'm going to hold off for 1 second, Erica. We're going to list them at the end, and we'll plug them in. But let's just solve algebraically. So we want to go ahead and solve for VI, so let's move the two underlined parts over to the other side by subtracting the whole thing. So on the left-hand side, all you're left with is 1/2 m VI squared, the thing that we're looking for. Okay, we're left with this on the left-hand side. Everything else we repeat on this side. Let me start with the first two that are already there. And then we're going to write these two on the right-hand side with negative signs because we're subtracting them. I don't understand what you're asking. We're just solving the equation. If this was J and this was K and you want to get this by itself, you would subtract J, you would subtract K. So we're subtracting the entire expression. Okay, the whole circle thing's here. We're subtracting these blue circles, the entire thing over here, to get this part by itself right here. Okay? So now we've kind of got it by itself, kind of, right? But I want to get rid of that 1/2 and the m. Let's get rid of the 1/2 first. How do I get rid of 1/2? Multiply by 2. So in your right-hand side now, watch what I'm going to do. Oops, let's go a little further. There we go. On the right-hand side, we're going to put a 2 here. We're just going to cancel the 2 and the 1/2 here, really. Put a 2 here, and then cancel the 2 and the 1/2. So we're multiplying the entire thing, both sides, by 2 to get rid of the 1/2. So on the left-hand side, the 1/2 is now gone. We have m VI squared. On the right-hand side, we have 2 mgyf plus mvf squared, because the 2, again, this 2 is getting distributed to every single term. Okay, within the parentheses, that 2 is getting distributed. So the 2 goes in front right here. The 2 and the 1/2 cancel, getting rid of it. Then we have another 2 here. And then this 2 and this 1/2 cancel, leaving behind just a negative kx. So again, I'm literally just distributing a numerical value in front of each term. I want to get rid of that m next. Erica?
You're going to divide by m and all the m's will cancel out.
Except for which spot?
The middle one. No. The kx.
Yeah, there's no m there. So watch what happens. Divide this whole thing by m now. So just get rid of this m on this side, cross it off, and put an m in the denominator. What you're going to notice is that the m cancels in 3 spots, but it doesn't cancel at the end here. So this is how you write this
So you're
answer.
still dividing that by m.
Yes, very good. So VI squared equals, now the m and the m cancel here. I'm canceling the m, not the g, the board's off. Cancel this m with this m. Cancel this m with this m, but there's no m here to cancel. So you still need an m in the denominator for that part. So it becomes 2gyf plus vf squared minus 2gyi minus kx over m. Notice everything the m is gone except for the kx there. Because again, all these m's here, here, and here dropped off from this m right here, but there was no m in the kx, so we need to include it in the denominator. Any questions on that part? Again, we're just doing advanced algebra. That's what this really is. It's very advanced. Now, we want to get rid of the square, so what do I do again? Square rooted. So just go like this now, please. Put a square root around the whole thing, put a plus or minus in the front, and you can get rid of your squared right there. And that's your final answer before you plug in numbers. Okay? Before you plug in numbers. These are being added together. You can't cancel those. Only if they were multiplying. So with this answer here, if we plug in our values, let's go through what we know. What was G, everybody? G is always?
9.81.
Thank you. What was YF, the final height? The person's height. It landed at the person's head.
2 meters.
2 meters. Again, YF was 2 meters because it hit the person on the head. I'm going to list it, just so you know. And you're going to plug these in on your own. VF was the final velocity, which we told was 12 meters per second. That was the velocity we wanted to hit the person with.
G is 9.81.
G is 9.81, which I'm not going to write. We know that. YI is the initial height, which was 8 meters? 7? 7, thank you. And finally, the K value in this problem, K value is given as 0.2 newtons per meter. The X value, what is the X value again? For these problems, not for projectiles. For these problems, where does the K come into play with the spring? How far it is what? Stretched.
The distance.
Stretched or compressed. It is stretched 10 centimeters, which is 0.1 meters. Finally, what is the mass? The mass is given as 0.003 kilograms, which is the same as 3 grams. Knowing those 6 values and the value of G, you can simply plug into this equation. You will get 6.73 as your answer. I want to know what the speed is, so I don't need the plus or minus. I just choose the positive answer. So the final answer for speed is simply 6.73 meters per second. Again, I don't care about the plus or minus. Make sure you're checking these problems as we go through them on your calculator, okay? A lot of people in the other class were plugging in and not getting the right answer. So if you plug in here and you don't get the right answer, you're making a mistake in your calculator. In case you're wondering, it might be useful just to put parentheses around every term. You don't need to, but that was an issue that people were having. They weren't using their parentheses correctly. Okay, putting parentheses around each thing. It might help. Okay? And then take the square root at the end. Do all the work on the inside. Do everything with the radicand, the number on the inside, and then get an answer, and then just take the square root. All right. Very tough problem. Very tough problem. Conservation involving every type of energy. The only thing we didn't have here was Q loss, the heat or the energy lost, the friction, which we're going to look at in the next example. This is probably the toughest you can imagine for a test example that you would have, okay, for conservation. You're most likely going to have an easier one to start, something where you have like, the skateboard going back and forth, where there's just potential and kinetic energy. Then you might have one with the spring shooting off. The next example we're going to do is a spring, but there's also loss due to friction, okay? So let's take a look at this one. An object with a mass of 4 grams is our last one for this section. An object with a mass of 4 grams is slid across the rough surface of a lab table. An object with 4 grams, or with a mass of 4 grams, is slid across the rough surface of a lab table. Imagine the coefficient of kinetic friction is 0.5. Okay, think back to forces. It's going to come into play here. If it starts moving due to a spring, and the spring has a stiffness of 15 newtons per meter. So again, if it starts moving due to a spring that's compressed 12 centimeters, so imagine you take a spring, compress it with an object at the end, and then it's released. Let go. It's released. How far will it have traveled when it is moving with a speed? So how far will it have traveled when it is moving with a speed of 4 meters per second? I'm going to do a diagram while you're writing the rest down so you can see what I'm talking about here.
So the stiffness would be X.
No, stiffness is K.
Stiffness is K. X is the compression, 12 centimeters. X is, remember, it's a distance, right?
Okay.
So look at your units, Gabby. See centimeters here?
Yeah, I know.
Here, that right away tells you it can't be
I
X.
thought you said okay.
So we have a spring. This spring is compressed. Make believe the spring looks like this now. Okay, it's been compressed to that distance. How far has it been compressed? It's been compressed 12 centimeters. You then let go of it, so the object is propelled forward by the spring's energy, and it starts to ride across the ground. So now the object is over here somewhere. It's not attached to the spring. The spring has pushed it off, and the object continues to ride like this. Until at some point in time, it's going to have a velocity of 4 meters per second at some instant. I want to know how far has this object traveled? What distance has this object traveled when it's at a velocity of 4 meters per second? Now, it's definitely going to come to rest after a certain amount of time because there's friction involved. But we're not asking how long or how far does it go before it comes to rest. Okay, but I want to think about that when we do this problem as well. Okay, we're going to think about that idea. So, let's begin. In the beginning of the problem, here's the initial sign. I see that there, is a spring that is compressed. So in the beginning here, you have some potential energy in a spring. I've compressed it fully, and then I let it go. So it's not moving initially. So what's the velocity in the beginning? So is there any kinetic energy in the beginning? Is there any height for this problem involved? Assume it's on the ground, obviously. Is there any height involved in this problem at all?
No.
So there's no potential energy for height. Okay? At the end of the problem over here, we know that there is some sort of velocity, right? Because it says it right here. So if there's velocity, there's what kind of energy? Kinetic. Kinetic means motion, so there's motion here, okay? So at the end of the problem, there is kinetic energy. Is there a spring at the end of the problem? Is this going to hit into another spring? So there's no spring energy at the end. And then, has the object gained any height at all? It's sliding across the rough surface of a table. Is it gaining any height? No. So there's, again, no potential energy at the end either. So a lot of things drop off here. Notice that?
So what's
Look at the 4 zeros. See all these 4 zeros here?
PES?
PES is the energy of the spring in the beginning. So there is energy in the beginning from a spring, and there is energy at the end from the motion, from the velocity. What causes this object to slow down? Friction. So what else is at the end of the problem, or what else should I put at the end that we talked about the other day? Q loss. Very good, Steph. So let's write our equations out now. So in the beginning there's PES, and at the end all there is KEF. But there's also some loss due to energy. So please let's write our Q loss here. This is where energy is going to come into play with friction here. So again, I know that I had a certain amount of energy due to the spring. At the end of the problem, I have some energy due to the kinetic part because it's moving, but I've lost some of that energy along the way because friction impeded my motion. So I have to account for that loss by putting our Q loss at the end here. Okay? Now, let's go into this problem, look at our equations. Potential energy of a spring is 1/2 kx squared. Kinetic energy is 1/2 mv squared. The question becomes, what is Q loss? Now, think back to section 5.1. So think about this, just keep in mind. This is something from section 5.1 we have to think back to. We're also going to look at forces for friction in a minute, which is from chapter 4. So this next test you take when it's on conservation, you need to know the old stuff, because it's going to come up. Okay? The stuff from work done, the stuff from Ff equals mu Fn for the force of friction, you're going to need to know that. The formulas are still on your test, but you need to recall that information, or how to use that information. Now, if I wanted to know how much work is done by friction, remember the work done, or the amount lost of energy, is always F cosine theta, absolute value of x. Okay, that was from section 5.1. Remember, this Q loss really means the work done by friction. So for F, I could actually put FF. What was FF stand for? Force of friction. Now, here's the most confusing part. People think the x's are the same on both sides. Let me really quickly go over this. This x over here, remember, is how far the spring has been compressed. This is for my spring energy. This x is how far the object has slid across the ground. So if you would like to, for the purpose of this example, feel free to do this. Instead of putting x here, feel free to call this d. Because in our diagram, I called it d for that reason. In the diagram, remember I called this d right here? Because I didn't want you to confuse that with x from the spring. I don't usually do that, but for this example, feel free to call that d. Now, I don't need the absolute value signs anymore on the d, but I do have absolute value signs around the whole thing. Because the Q loss had absolute value signs around it. I don't need the absolute value around the d, because the absolute value of x is d. Remember this a minute ago was this. That's what was there. But the absolute value of displacement is distance. So I can just write distance there. Here's the issue with this problem. K is given. We know that value. The compression distance is also given. We know that. We know the mass of the problem. We're also told 4 grams. We're told the final velocity is 4 meters per second. We can think about theta, and this is going to be intuitive here. The object's moving this way. Friction is acting this way. So what is theta between my hands? 180. That's what theta is. The distance we're trying to figure out. So the only thing we still need is FF. If we can figure out FF, we have everything except for D. See what I'm saying right now? Again, given, 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 we need FF, which we'll figure out in a second, to get D, which is what we're looking for. Now, if you want the force done by friction, remember, the force of friction equals mu times Fn. That's why you're given that mu in the beginning of the problem. In the beginning of the problem, you were told that the surface has a mu value of 0.5. That's where we're going to use that. But the question now becomes, what the heck is Fn? How do I figure out Fn? Which way does Fn act? Up and? Up and down, right? Fn always acts up and down. So what's Fn in this problem, Emmett?
Well, since it's not moving up and down, the object would be N equals mg.
Very good. Take a look. If I have the weight of the object acting down and the normal force acting up, like so, and I want to figure out what the normal force is, it's not moving up and down. So I can say negative Fg plus Fn equals ma, but a is 0, so I put a 0. I move the Fg over by adding it, but as Emmett said, Fg is defined as mg. So Fn is simply mg in this problem. Again, in this problem, that's what Fn is. So we take that and plug it in right here. So this becomes mu mg. That's what Ff is. Again, Fn was solved for as mg. We plug that in up there. It becomes mg here. So we have mu mg equals Ff. Let's take that now and plug it in. Hold on. Take mu mg, plug it in right here. What we're going to get, and we're just about done, what we're going to get for our equation now is going to be 1/2 kx squared equals 1/2 mvf squared plus absolute value mu mg cos theta d. And these are all times. Everything's times in between them. So for this kind of a problem, we know k. K was given as 15. We know x. X was given as 12 centimeters or 0.12. We know the mass is 4 grams or 0.004 kilograms. Vf is 4 meters per second, all given still. Mu is 0.5. The mass is 0.004. G is 9.81. Theta is 180. We can solve for the only thing that's missing, which is D. Your final answer when you solve for D, okay, when you solve, oops, let's go up a little bit. When you solve this equation for D here, you're going to get D equals, and watch what I'm going to do. I'm going to take this whole expression right here, subtract it over here, and then to get D by itself, I'm going to divide by this entire thing right here. So by subtracting that, I'm going to have 1/2 kx squared minus 1/2 mvf squared when I subtract it. Then I'm going to have this whole thing left over. I want to then take this quantity and divide by it. Mu mg cosine theta, and please put that in your absolute value bars, because we can't just ignore them.
Why is that under there?
Because when you move this over, Steph, this is going to be gone, right? And you're going to have minus 1/2 mvf squared on the left side now. These are multiplying, so I want to get rid of these things. This is like one giant coefficient in front of D. How do you get rid of a coefficient? You divide. So we divide by mu n g cos theta. That's in the bottom here. Your number, check on your own, will be 3.87 meters. Okay? Tomorrow, please, finish your lab up and work on these problems tonight. See how you can do on these problems. Yeah, you did 1, 2, and 3 already. I know that because that was your assignment during the week. Finish page 4 of your lab for tomorrow to turn in and work on these problems. It's on Moodle already if you want to look. Okay, but there's 3 problems here. They're a little tricky. Don't give up on them right away, please. Okay, think about what we've been doing with energy before and energy after. We can go over them tomorrow if we have questions.
Have a good day.
Have a good day, guys. Good job today. Well, way to focus.